Hello and welcome back to Compiler Programming. Today I'm going to do something a little bit different. I wasn't able to record videos because of some personal reasons for a bit, but I continued to work on the compiler. So today I thought I would go through the commits since the last video, which was episode 186, and I would just talk about changes if they were interesting, or if it's something like worth talking about. Some of the commits are just very simple, but we're just gonna skip them, and hopefully this will not take forever. But let's just dive right in, and we'll take the first commit. Let's open it up and let's see what it's all about. So what is happening here is that whenever there is a function that is a compile time one, so let me maybe open the code here again, and that would be source. Actually, let's open std and prelude. Right. So let me take a look at what we have. We need a function like this, and that is maybe okay. But maybe there is something more interesting. Let me look. Yeah, I think that's a great example. So whenever we have a function that is a compile time, so this is a fat arrow here, which denotes that this is kind of called immediate. I think in something like C++ terms, that's const eval. But anyway, so this returns a struct. And previously, what would happen is we would copy that struct twice. So the first copy was happening whenever on the return of the function, we would copy it into the like a temporary memory allocated for the return of this, and then we would copy it from temporary memory to the actual location in the compiler where this belongs. And this cleanup essentially just takes care of that by changing how the trampoline works, and to, as you can see here, it's sort of dereference a memory and copies right away, and then when we construct this memory, we directly put it where it's supposed to be. So that's just a simple thing, but it's very nice for performance long term. Okay. Make sure static params are correctly mapped to defined ones. This was a very interesting thing to debug. So what would happen is whenever we have, so in the last video, I take a look if you haven't seen it, I added this thing called static params. So you can add like an add sign before a parameter in a function. And this parameter is essentially considered static. So it's like it turns this function into a generic one, and it bakes this parameter into the body. So it becomes this like a statically known, compile time known argument. That means that it's not actually passed as an argument to the function anymore, but the code that was doing the calls was not aware of that, so it wasn't correctly dealing with it. And here what I did is that whenever we map this sort of real call parameter that is in machine code to the one that is defined in the function, we now have an index. Here you can see parameter index, and we save it out so we can later use the right thing here. That is all that this pull request is doing. I don't think there is anything else. There is explanation of what I just said. But yeah, this was tricky to figure out, but rather easy to fix. Okay, what's next? Right, so here was just a bit of a spree of trying to move more stuff to user-line definitions, which is going to be interesting once we get to the end of this review, because all of this was moved back. But for now, we can say that this definition of a using operator was moved to userland by doing this. not much. It's just like sort of a cleanup work using already existing facilities that are in the language. And that's the same for return, so I'm not gonna look at that. And now this is a debug thing where there's just a better debug thing where we can now correctly print functions that don't have a defined return type. Instead, they infer their return type. Okay. Prepare match overload candidate for different literals and instance handling. Right. So I don't think that this was in the end required, but it wasn't a bad change either, so I probably just kept it. In a sense, this just moves some of the code up in a function. There is no logical change for this, so we can skip this one. Okay, what is happening here? Right, this was a big thing that I wasn't sure about, how this is supposed to work. So when we have like runtime functions and compile time functions, there is a question of what has higher precedence and what can be called from where. And I think at some point in one of the last videos, I decided that if you are already in a JIT context, you can call these functions, but they turn out to be rather ugly and annoying to deal with, because you would constantly either get into a situation where you had two overloads that could be called or none of the overloads, and it was just a bit annoying. So I decided to simplify this, and now this literally just means that if both of these are compiled unknown, then this overload will be called. If not, then something else will be called, and you also can, well, not from the source code, but at least internally it's possible to specify that a particular function belongs to either runtime or compile time, and then it's callable there regardless of whether arguments are known or not known. So this was the change here. Is just a auto-generated code, which is not interesting. But the main change is here, where basically, yeah, if the function is marked as compiled unknown, and arguments are not static, then we just say, okay, sorry, we cannot even try to call you. Like, this will never match. So that is that. Yep. I guess the rest of just is a cleanup. Oh yeah, one of the side effects of this is that now we have this set of functions that are defined defined by the compiler to deal with i64 numbers, but these functions are only callable from the JIT code because the compiler defines them, but it doesn't provide like machine code that would be able to output to the executable. So this is now nicely packaged in an inline module, and if you are in a low-level implementation inside of userland, then you can use that. But for like regular stuff, the custom implementations I use that can generate x64 assembly and be used correctly. Yep. Okay, what next? At compile time, use built-in math implementations. Okay, so that makes sense. Here we are just using what is provided by the compiler if the arguments are compiled unknown, because that's more efficient, and it also is allows for easier bootstrapping of the rest of the code. As you can see, we can remove some of the stuff. Okay, what is next? Fix a type used in tokenization. Yeah, that was just a bug. These types had the same size, so everything, like the same size and same layout, so everything worked, but it was actually incorrect. Okay. I'm not sure what exactly was the reason for that. Maybe I should have added a y in here, but yeah, in reality, it doesn't really matter. Yeah, I'm not sure why exactly I did this. It's probably part of some larger commit, but it just changes basically that we previously we had expression with a single element, but now we just pass this single element directly. Nothing really changes in terms of the logic. Okay, fix possible infinite recursion when printing types. Yeah, I remember I ran into that. Basically, now there is this thing that if level is more than 3, then ... because if you have a type which contains a pointer to itself, or like it's an indirect cycle, you can very easily end up in a situation where you would end up in infinite recursion if you don't have something like this. So just standard stuff, but it was missing. Now it was there. Okay, I think I skipped this one, but it is what it says on the label. We removed a name field because it was almost never filled, and it was also annoying in certain cases, so just like it simplified things and it didn't really change anything interesting. The only thing is, and this is why I had to introduce that check for recursion, because now the types have this much nicer printer that is recursive, so you can say and see anonymous types and so on and so forth. And this is why I could remove the name, because like you just will see the whole type anyway. Okay, I think we can go back, and now we see more stuff. Still in December 20, so there is quite a lot to go, but let's see what we can do. There is a bit of a gap, I think, after this, but right. So this is where one of the interesting commits. Essentially, what it does is it adds support for using types as structs or as modules more precisely, and store some fields in them. So let me scroll and find where was this actually done. Let me find this place I'm looking for. Right, so maybe going to the code will be more visible. So define enum. And essentially what it allows us to do is to have this special module for an enum, and we attach it to the type, and then we define symbols for each of the variants of the enum, at least the ones that we generate from the C side. Right now there is no way to create new enums on the userland side, but essentially it would be sort of exactly the same code. It's just that it will need to be implemented in the mass itself instead of being implemented in C. Maybe I will use the same implementation, it doesn't really matter, but the main point is the functionality is now there, and this was a bit awkward for a long time, but I kind of like this approach. I think this is something that can work long term, but I'll see as I use it more. The rest is just more or less plumbing and support for dot operator. So this is the code that runs when you do like foo.bar, and bar is, and foo is now a type. Okay, next. Turn import in the prefix operator. That's pretty much what it says on the label. Previously, I think it was a function. Yeah, previously it was a function, and now it is an operator that just applies to the argument after it. Nothing really fancy. just expanding more of what was there before. Okay. This is a bit of a cleanup because import was moved to be an operator and it's defined earlier. Now this internal keyword, internal module I use for accessing sort of compiler things can be defined inside the userland, and it allows to get rid of this awkward definition inside of the compiler. This one is a bit interesting. So I thought would be neat if the comma was actually defined in userland, and this is just some metaprogramming definitions. I added a comma in here, and now it is just a regular operator, and we don't need to define it in here as well. I think it is similar to something like return, what we saw already, but I think it turned out pretty good. Okay, this is just a rename. That's not interesting. This one is pretty cool. Eventually, I did a sort of a different approach on how to do this, but I like this one because it is mostly implemented in userland. So as it says in the label, when we have enums, it's very nice to be able to say x equals and .foo as a enum variant. Almost all modern languages have this, and I would want to have it as well because I think it's very convenient. But one of the problems with this is like how they do it. Obviously, all of the modern languages, they sort of hard-code it in a compiler. I didn't want to do that. So in mass, there is such a thing as named accessor, which is also just defined as an operator. So whenever you have dot and then followed by a symbol, like dot is a prefix operator, it can either be prefix or it can be infix. When it is a prefix, then it creates a named accessor, which just stores, it's just a struct that stores a symbol inside of here. And now I can do an overload, which is implemented as an intrinsic. And this is not the prettiest piece of code. I definitely have more ideas how to make it nicer, but in a sense, it is a bit limited by the C API that we have. But it was an interesting test that this actually works, and it does sort of what you would expect it to do. It builds on the one of the previous commit that we saw about adding modules to the types. So here we access this module and we try to look up the symbol that is stored in this named accessor, and then we forward it to the basically to ourselves, but with new arguments. Yeah, and as you can see, this allows to say equals dot windows, which is kind of neat. But it had limitations, so in one of the last commits that we will see, there is a different implementation of this that is more robust. Okay, let me drink a bit of tea. Okay. Simplified generic equals handling. Right, this was just remnants of the stuff before I simplified compile time versus runtime overloading. And this was supposed to be probably a net commit, but I didn't make it. So here I'm able to make it slightly simpler. This is nice commit. Didn't really change any behavior, but basically in meta definitions, I add these underscore blah blah padding fields because I want the padding to be explicit in C structs and know when I add padding bytes, and not just because of the size of the struct, but also because it needs to be handled in a certain way in the compiler itself. But with this, they are no longer exported to the userland. And what that means in more practical terms is that because in the userland, so if we look at here, Yeah, if you look at something like this, so this struct actually has some padding bytes. And if they would remain as fields, because I do actually exhaustiveness check on the fields, so like you have to provide all the fields that struct has in here, I would need to say like blah 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 padding and then 0, which is super annoying and unnecessary, but it was just something that was an artifact of the way the C and the master runtimes would interoperate. So yeah, with that change, that is gone. They are just no longer exported, and it's a simple like string check. It's not very robust, but I know what's supposed to do, so it's fine. And even the thing is, even if this fails, like it doesn't really break anything. It just at some point I will the mess compiler will complain that, oh, you haven't assigned the padding field, and I know that I actually messed up and didn't do this correctly. So this was a really nice idea, and it was a simple change. Okay, December 22nd. Generalize and packed storage handling. Okay. So this didn't really go anywhere, but it was a good change regardless. So there is this concept of unpacked storage in mass, and the reason it's there is because in x86 64 system 5 I don't know, API, you have this thing where you can have a struct that is actually stored in 2 registers. And if you access a field of this struct, you need to know how to correctly slice out of one of the registers. Like it can never span across the registers, and there is a check somewhere around that. Yeah, so there is a spanning, right? So you can never have like a piece of data of the first register and a piece of data of the second register, but you can get like the first half of the second half of the register or something like this. And this is the code that deals with that. As you can see previously, it was sort of hard-coded to be... I know here it still says states what it is. So it's hard-coded to be 2 registers, but the actual algorithm here technically could be ready for more registers. And I think in the next commit, I did that change where disjoint storage now doesn't care about registers and can have any amount of things. So theoretically, I could extend this, and I could say that in my calling convention, if even up to 4 registers can be used to pass a single struct. I think it would be something interesting to try out, but the real reason I wanted to do this was because of static stuff. So I wanted to have structs, part of which would not be known to be static. There is a very different way how it's handled in something like LVM, but let's see how this evolves. So this is a continuation, essentially, of a previous thing. Now unpacked is called to disjoint. So this means that pieces of memory are not next to each other and then might not even be in the same memory. So something can be in registers, some can be in memory. And technically this should all just still work as it did before. So yeah, this is generic thing. It didn't really increase complexity, in the sense it might have decreased it in a couple of places. So I'm kind of happy how this turned out, and we'll see if I can make use of it later on. Okay, fix printing of float into row types. Yeah, here I forgot, or I unnecessarily divided by 8. Fix most casting when passing arcs to trampolines. Okay. Yeah, so this is a bit of an awkward thing where if you pass, so this part is about passing, like copying from a static to static, because unlike many languages in mass, the fact that something is compiled to unknown does not automatically imply that it is const. So you can still modify compiled unknown values. Like constness is separate, it's not very well fleshed out. It's kind of a bit of a hack at it on top, but it is there. The point is, if you do copy into the compiled unknown value, you actually need to do memcopy, and this was missing, so now this is there. And I think additionally there is some other stuff. Yeah, so what this does is, I guess it's easier to look at the code. Well, something like this. So you have 8 here, and 8 is an I64 literal, but the actual target type, so in this case it is I64, but it might have been an S64 or something like this. And if they didn't match, these types didn't match, we needed to cast one to another. Also, the same thing happens for tuples. Yeah, something like this probably is a better example. So this is an anonymous tuple. It has a correct, sort of correctish type, but we still need to cast it. Previously it was sort of happening, but wasn't really. And now this is way more strict. So whenever we match an overload to be called, we go through all of the arguments, and if the types of the arguments of what we have and what we match don't match exactly, like this can happen, is that because of some casts that are allowed, we try to force them to be the same. So here we just create some memory with a new type, and we copy over whatever we had to the right location. Yeah. Okay. I think that's about it. What's next? Next is use mass allocate bytes from descriptor and a couple of aliases. That's not really interesting. Yeah, I just had a helper and I realized I wasn't using it everywhere I could be using it, so that's just a nice cleanup. This is an interesting commit. I'm not sure it will stay that way, but the idea is that, like, I don't want to have a string type defined in the compiler. But the big question is, what should be the type of the function literal? One option would be to make it a fixed size array, and maybe that is still what it's going to be. But for now, I decided it might be easier to just say that the type is actually what it was before, except for the brand. So, like, this is sort of an anonymous tuple that has bytes and length stored in it, and that means it will be assignable to anything that has bytes and length and that has correct types. So the bytes is a pointer to characters, and length is an I64 or U64, whatever, just as long as the sizes match. It involved to add a helper to make sure that we can call sort of built-in procedures that would accept this type. But now technically it's pretty easy to accept this type in any of your functions and do whatever you want. I'm still not sure that's the best version of this, but we'll see if that's ends up being the correct way to go about it. What's next? Oh yeah, this one. Let me scroll so I don't miss where I am. Array type constructor should be callable at compile time. What is less than label, essentially. Yes. So this is an interesting change. And previously, what it was possible to do something like, who is my function? And my function didn't have to be an immediate. And now it is required that my function is defined to be sort of like this, with that arrow, so it immediately returns. And if you want to force the evaluation, you could always do that. And this is a compile time evaluation, so now everything is fine as well. I think it's just a more robust way to do it, like when that gives you more peace of mind of what is automatically compile time, what is not automatically compile time. And you can always like define your own very operator like this if you really wanted to, if you think that typing this is too much. So it was just a simplification, as you can see in the compiler land, and it's something more robust, I think, but it removes a bunch of code, which was pretty good. Next. Yeah, so I had this concept of startup functions. It was developed in one of the videos. You can probably even find it in the list. But I realized that I wasn't really using it except in one place and not even really there. But it was quite messy. As you can see, like there is a lot of stuff. There's a lot of code that was doing that. And I thought that, well, if someone would want it, I rather make it so that it's possible to implement this in the userland if necessary and not inside the compiler. So it was just gone. Okay. Fix skipping as field padding when exporting. And yeah, this was one of those things where I accidentally did export padding, as I mentioned, but I caught it when I tried to assign and I fixed it, so that was pretty good. Accept the source range. Well, this is a debugging thing, just making sure the error is reported in the right place. Nothing really fancy. Here, I realized that I never actually used this, so the field is gone. Remove an unnecessary dereference when assigning arrays. What is that? Right. Yeah, this was just not doing anything. We literally never got to this code with a reference. It was all unwrapped earlier, so it was just useless. Okay. Only the reference and placing pointers in masked handle field access lazy. Right. So I don't remember exactly what was this about. I have a vague memory of this, but it has to do, yeah, with just at which point we decide that we need to unwrap something or we don't need to unwrap. Yeah. So here we previously would unwrap both the real runtime pointers and implicit pointers, and this change just checks that we only do that for implicit pointers, which will actually be gone in one of the follow-up commits, so you can ignore if you don't understand what that is. Okay. Remove no longer use value may be the reference. I always love commits like that, when you realize, wait a second, this function is just not used. Great, we can get rid of it. This is another thing that was slightly awkward. So I tried to be clever, and there was this pair of macros that allowed to say that if the value feeds into 64 bits and you don't need to allocate an extra pointer, you can pack it inside the pointer. Like, I mean, all of it is great, and I might bring it at some point, but for now it was just introducing extra code, and it wasn't doing anything. I barely measured any difference once I added it, like once I removed it, so who cares? This I think is a very simple change where, yeah, so apply or empty space operator or juxtaposition, I think how it's called in Haskell. Basically, whenever you have two values next to each other, this needs to be dispatched operator. Previously, it was more hard-coded. Now it's less hard-coded. Nothing really interesting here. Simplify token dispatch operator. Let's take a look at that one. Right. Yeah, so previously it was trying to figure out how to better provide source range for this for the operator, but it was a bit heavy-handed and wasn't resulting in a good error range anyway. So I thought, okay, we'll just gonna report the operator itself whenever we talk about the operators in errors. I think this is pretty much what it says in the label. There is only one place where this was used, so you know, we were able to fold it in, and that simplifies. Like, this shows you that if compiler does it, inlining is great. If you do it, it might be even better. But yeah, just simple commit. Let me get more key. More simplify speed up. So what is happening here? Right, in here we basically switched from scanning to the end of the line for a double semicolon to checking that the double semicolon is the second token on the line. So whenever I have something like this, right, previously we would technically match that and then realize that it didn't match because we don't support complex expression on the left hand side, but now it's directly matching what's supposed to be matching. That's, I think, all this commit does. In the common handler parse common equals, yeah, okay. So basically, previously the expression, as it says on the label, the expression to the right hand side of colon equals was parsed differently, whether it was in the at the global level or inside the function. Now this commit just brings it all together and unifies it. So as you can see, we remove it from two sides and we add it to the common code. Turn this into an operator. This is continuing the cleanup where there is less specific code in the compiler and more general code where now this operator, so previously it was a custom statement matcher, now it's an operator that just returns void. So this is something I think I should actually talk about a bit more. That mass currently is very like an expression language. So everything is an expression, and then to decide whether something can be used, like so in C you can do something like this more or less, right? You can take the assignment is an expression as well, and you can it returns this left hand side, and then you can do operations on the left hand side. It's not actually that way in mass. So yes, assignment is an expression, but it is an expression that is defined to return void. Later on, I think I will introduce a special type that's not void, but like, I don't know, never or something like this. I'm not sure. But the point is that this is disallowed. It still returns something, it's just that something is not something that you should ever try to do any operation on unless you are doing some compiler magic. But from the perspective of the parser and everything else, this is just an expression. And this is what this commit does. Refactor generic parameter parsing. This is a quite involved commit. It streamlines how the arguments are parsing. Previously, it was a bit of a tangled mess with a bunch of if, else's, and the code that was like you would assign a variable over here, and then somewhere down in the code you would use it. Just a bit too messy to work on, so I streamlined it in like this filter style thing where, okay, we try this, okay, if this matches, and we return immediately. If it doesn't match, we error, and then we parse and parse and parse. So this is like a standard parser basically implemented here, just for arguments. And I think it did quite well because now it's way more readable, and I like these new inline comments that I added that just show which kind of argument is this parsing. This is the same for different kind of parameters. I will not even go into that. Instead, we will jump to the next thing because there is still quite a lot to go, I think, and we need to speed up. Finish refactoring token match argument. Yeah, this is continuation of the same I was talking about. This is the rename of this, and remove unused function. What it says on the label. Mark very lazy payload as const. This is a thing where I realized that I never was modifying the payload of this, so why not make it const? It's better for everybody, and it's nicer to deal with. So yeah, this is just a pretty mechanical change where everywhere now it's const. I know different people feel very differently about const. I still think it's very useful, or at least for what I do. Remove unnecessary immediate forcing. Right, so this was the remnant of the change that we also saw regarding the, I think somewhere here where I had a different structure, but now these things are required to be compile time, so we don't need to do this over here. Okay, remove unnecessary token parse single calls in, I think this is in the same vein. Yeah, exactly. So this is just something that should not have been there, and it was required at some point, but then they changed how parameters are passed and it wasn't required anymore. So just clean up. This is just me adding this stuff. So to remind you, this was implemented, I think, in a couple of videos ago, where well, there is this type constraint. So this X is generic type, and any pointer type will work. I think in traditional languages, this would look something like star T or something. And it might still be that at some point, but for now, it is like this. Okay. Add support for static generic param in intrinsic. In reality, as you can see, this is just a test, so this was already working just fine, but I wasn't sure, so I tried it out. Compile time with static params. Yeah, this is something I added test, and I think it wasn't fixed for a while. And when we get to the point where it is fixed, I will explain what the deal is there. Separate function instance caching from info to arg mapping. Right. Yeah, so this just essentially moves this condition. So a function can either be a literal or it can be a function pointer. And here the check was if it's a function pointer, then we don't have to do anything. But if it is a function, we need to compile a function. Oh, not really, we need to create like a header for the function. And we need to correctly assign all the parameters, especially if it's generic. And then we will return a pointer type. And this just splits it into two functions. That's it. Use decide signature. Right, so this fixes the situation where you have something like, is there a test that added? No, not really, but in here we have something like this. No, yeah. So in situations like these, or whenever you pass, yeah, here callback to something, we need to choose which overload or which on how to convert a generic literal into a function pointer, and this makes sure that this is done correctly. That's all this code does. What is next? I'm a bit missing here. Ah, yeah, here. No. I think I missed this one, but it's not really interesting. This is just a continuation of one of the previous ones because I split these two functions, one that deals with pointers, one that deals with literals, and now because I know that in the script mode, which also was added on the video, which you can check it out, because we know here that this is a function literal, we don't need to go through the one that checks if it is a function literal, just slightly simplifying stuff. Right, so these checks, we can look at the test. It's nicer when there is a test associated, but essentially, if you have a generic parameter with defined constraint, but the type signature of this constraint is incorrect, we expect to have an error, and that's all this does. Okay. What is happening here? Right. So this is essentially just an optimization. I think it will be a bit too involved to describe what exactly is happening here. But in 2 words, whenever we need to generate a JIT function, previously we would require to know what are the exact arguments for that function, but now we can sort of have pass this precompiled or pre-calculated information about the function that also includes the types of the arguments instead of the real arguments, and we use that to cache, which should result just in better caching, and also in release builds we can avoid some of the stuff, some of the work. It's not interesting. This is about the strictness. So the brand is something that's usually called distinct in some languages, but basically if you have like you have an i64 and then you want to have a specific kind of i64 that, for example, holds I don't know, seconds, you can add a brand to it. There is no userland API for that yet, but because you have access to types, you can just do it yourself if you want. And this just checks that if we want a full type match, we would explicitly check that those types do indeed match. Yeah, so this change now makes it so that if type is marked as raw, as in these are just raw bits, bytes, whatever, they will match with anything else as long as they have the same size. And this raw type is not something that you should be using a lot in your program, but it is very useful for implementing sort of the basics, what you would expect in a language, but implementing that in the language itself rather than having it inside the compiler. This is more or less the failed experiment. It didn't really do anything. It just changes how, if I have a compile time function, I generate a bit of JIT code. Then this JIT code, it just assigns the return value to some pointer memory that we pass in a struct. And this changes it from being passed in a struct to being passed as a separate argument. This is supposed to have improved things. It really didn't, but didn't make them more complicated either. So in the end, I just decided, like, okay, I don't care. Maybe I'll have a better idea later on. Just removing stuff, not interesting. Specialized Trampoline proc compilation. What is happening here? All right, yeah. So I was on a bit of a spree with the trying to optimize the compile time call or trampoline calls. Again, to remind you, these are these kind of things which are happening at compile time, because we generate an extra wrapper function that has the calling convention of what the compiler expects, and then passes the arguments to the right registers of the target function. And previously, as you could see here, I was generating this as a string and then calling tokenize on it here, and just letting the regular machinery handle it. But this was, first of all, not as fast as it could be, and more importantly, that would mean that I could use only very limited set of features that are by default exposed to the userland, and it was getting more and more awkward as I sort of pushed more and more features out of the compiler core. So I decided to just bite the bullet, and instead of generating text, I would sort of generate the operations that are necessary to copy the arguments in the right positions directly. And that ended up being not that much longer than it was before, but it definitely became faster. I think I got like 5 or 10% performance in some tests, and I think this is way more robust long term, and there is still stuff to optimize here if we really wanted to. Okay, almost up to here. I think this is just about void. Yeah, here we just check that we correctly handle zero-sized void values. Prepare operator definition to accept tuple. We can just say if we ignore that, operators end up something completely different, so I will just ignore this, because we're coming up on some actually interesting stuff. Here I realized that this test was testing bullshit in here, and I added more tests to check that, for example, we support underscores, which we do, but something like foo underscore and then number should have passed correctly, about 0. Just a bit more tests for the tokenizer, which will be important if you saw the next commit. And here is the next commit. Implement a handwritten tokenizer. And this is something I was thinking about for a while, and basically I liked the speed of read to C, which is a lexer or tokenizer generator that we were using. But the thing about read to C is that it is, as with any generators, it is quite awkward to customize it, and you have to regenerate this. I could have tried to like put it better into the build process, but it's only available on Linux, so I need to specifically compile it for Windows, and like it's just like this whole thing of complexity that wasn't really helping much. But as I said, I did like the fact that it generated really fast tokenizers. Because when I added it, I think it shaved like 100 or 200 milliseconds on big tests, which is a lot of time. But there is this technique. I think the guy that stb library, what's this, Sean, his name is, yeah, he's nothing's on GitHub, Sean Barret, yeah. So if we go to this website, sorry for the bright light, in here somewhere we can probably find something along the line of lexer, tokenizer. How do I see? So I see C processor. There is basically a thing about how to create nice tokenizers. I unfortunately cannot find it right now. I will try to find it and link it in the description in the video, but the point is he has some advice on building fast tokenizers by hand, and I had a lot of similar thoughts, took some ideas from what he wrote, added some of my own, and basically implemented this tokenizer. I think I would need to do a different video on it. If you think that it's interesting for you, just write me a comment like this video and I will know that I should do this. But the basic idea that exists in this tokenizer, so we move byte by byte, right, through the string. This is what you more or less have to do when you're trying to split the text into multiple pieces, all right? Imagine we go through this stuff. But what this thing does is that whenever you come across a character, first of all, it checks if the character is not UTF-8, because we only expect UTF-8 in strings. And if it's not UTF-8, it tries to figure out what is the category of this. And category is a bit of an abstract concept, but here you see those categories. So you have ID start, you have space, you have special symbols, and you have other stuff. And so the idea is that instead of doing a switch essentially on 128 values, you first take those, or 256, you take that byte, you collapse it down to a bunch of categories. So in this case, what, 8, and then you are able to switch on it much easier. So you can see, okay, if a category is slash and previous category is slash, so we know we are in the command. And here we check that, okay, if, like, for example, we started with the ASCII character, and then we have something called continuation mask, and continuation mask says that if we started with an ASCII character, and the next thing is an ASCII character or a digit or an underscore, then this is an identifier. And if it's not, we actually do the work here. There's some extra stuff on handling numbers, but all in all, this is a pretty compact thing. Like, as you can see, it's what, 320 lines, and this is completely equivalent to what was generated by Re2C. It has basically the same performance. So I really like how this turned out. Yeah, I know this is a very quick sort of summary. So if you would like a more detailed video on how this works, let me know in the comments and I will consider creating one. Okay, we can close all of this. I think the next few commits are refining on the tokenizer. First, we just remove the old one, and you can compare that even as a source code, like, so I went from 180 lines to like 320, which is a bit more, but if it also gets rid of the whole extra tool, and as you can see, the generated one is even larger. So there is like this very large switch. So I think it was a very good trade-off. This just moves some code around, not interesting either. More tokenizer simplification. I think I will skip all of this, because if I ever do the video on tokenizer, I will just fold it in there, but right now it's just more and more simplification, or actually more maybe complication of the tokenizer, but just work on it any further. Okay, more tokenizer stuff, more tokenizer. I'm gonna skip all of it. I think this is still tokenizer, and now we are outside of it. So one of the things I started to do recently is I realized that in cases where I know how moving some stuff to userland looks like, but right now it doesn't provide any benefit, I would move it back into the compiler. And this is one of those things where I put this empty space operator back into compiler, because it just makes it much simpler to develop the compiler, and that is more important at the moment, because I said I proved that I can move it out, but it's just like it's easier to keep it in for now. That's all it is. This is an extra thing, so now you can do something. So you can do something like like this, and this would be essentially a function called through this kind of stuff. Nothing really interesting. Yeah, so what this does is, again, if I have this stuff, it makes sure that this is always parsed first before we do any dispatch, because in reality, all the cases I saw is like that. We never really want to not parse it from cases we have. Like if you have something like 1 + 1, so this would be parsed first before trying to figure out what is the meaning of this expression. That's all this commit actually does. And as you can see on the label, yeah, we just always parse this instead of just getting it raw. Turn some type blah expressions into casts. Right, so this is more in application, and I actually have it used in the place. So this allows for these kind of expressions where you have a type on the left-hand side and then something on the right-hand side. Internally, this is literally just the same as writing casts, you know, like this. And this is just a nicer syntax, and this exists in C++, in Rust, and some other languages, so I wanted to have it as well, but this is more flexible here as well. Just a change of data structure. Previously, statements inside a block were, here you can see they were array, and now it's linked list. Now generally, linked lists are usually slower, but not in particular in this case, because you avoid this an extra copy when you are tokenizing. And all in all, I measured it was slightly improved, I think, maybe like 1% on a large file. But yeah, all in all, I think it's nicer to not copy memory when it's not necessary. This is a kind of interesting thing because previously there was a problem. And the problem was when we would have stuff like so if you had a C type that looked like this, where you have some kind of stuff here, and then you had a union, there is no distinction between unions and structs in mass. So the way that works is similar to how JI or JI does it, where these fields are just sort of explicitly placed in the same location in the struct. So at a particular offset, we have this field and this field and this field and this field. And previously that is what was happening. So when we try to assign like two unions to each other, or when I try to assign something like this, so this is also a tagged union, right? There is a tag, and then depending on the tag, you can see here we put some stuff into it. If I try to, or here, if I try to assign it, it would require me to put all the variants. And this was very wasteful, it was causing problems and all kinds of things. But for a while, I didn't really know how to deal with it because I don't actually have the information that like something is a union. I just had the offsets of the fields. So the logic that ended up being implemented here is kind of tricky. And maybe I can sort of try to show it in a comment. So if we have like a union of, I don't know, int x and then, or let's say s8x and u64y, and I try to, and this is a foo, and I assign it to like x5 in C terms, right? So what I end up doing is I end up scanning the fields. I know that field X and field Y are both on the same offset, and I allow to omit all the fields that are overlapping. So in this case, X is overlapping Y by 1 byte, but doesn't matter by how much. And because it's overlapping, that means that I don't have to specify Y on this right-hand side. This so far looks to do what I want. Maybe there are some weird, like I can see cases where it wouldn't exactly work maybe, but not really in C definitions. So far this works pretty well. The way that works internally is, as you can see, when I assign a field, I just figure out what is the range of bytes that this field is occupying, as I said. And then right now, just inefficiently, I go through all the fields, and if it overlaps in range, I say that field is already handled, don't worry about it. And then I check that all the fields have been dealt with, so they either have been skipped like this or properly handled. This was really nice thing because, as you can see, I could much nicer deal with assignment of structs, and now this feels way more modern than C89 style things that I had before. Okay. This is just applying the same pattern in more places. As you can see, changing from dot something to assignment like this, which is very, very nice, I think. Just, it's not that it's changed much, but I think it makes the language feel more modern and developed. Support encoding local storage with offsets. Last commit before in the last year. And here, essentially, this backend change, where if I have a label, previously I was not able to specify offset from a label. So and this just adds that basically. And there is a bunch of propagation for the whole compiler of this offset from label, when finally it just is added. That's pretty simple, but as with anything that has to deal with assembly, this was pretty finicky to get right. There were a lot of crashes in between of where I figure out exactly where I need to add this patch, and if I do it too early, that's a problem. If I do it too late, that obviously is a problem. So it was a bit of a thing. What is next? Next we have support exact static parameters in trampolines. Yeah, again, if you don't know what static parameters are, I implemented it in a previous video, episode 186. And here the thing is that when something is known to be static, it is now defined to be static. I know that sounds super obvious, but that code here was just missing, right? That's handled that we correctly do this kind of stuff. And now it is correctly supported. So there were a couple of disabled tests that I mentioned, and this just fixes those tests. And I think it was this label storage thing was actually required for the static parameters because you would, if you get a struct as a static parameter, we know it's label, like it's living on a certain address identified by a label, and you have to take offset from that address. Just to rename, not gonna look at it, also not interesting. Non-block bodies for issues with predefined headers. Right. So this will come up a bit later, but essentially, if we look at standard.linux, it allows to do this kind of stuff. So here, signature is a function signature, and then we have a body, which is defined in line as an intrinsic, and we can compose functions like this. I could have added some kind of function to do that, where you pass a header and a body, but I thought this is also kind of neat. Why not? Okay. And then we have a couple of things regarding syscalls, what you just saw here. Essentially, I realized that syscalls were a bit of a weird appendage to the compiler. And there was a bunch of code that was explicitly dealing with them, and there is still a bunch more to get rid of. But this sort of starts dealing with the stuff. And the way it deals with it is that instead of code, yeah, for this first commit, I just move a global function syscall. So you can see previously it looked like this. You would just put this header function and then put syscall, and it would automatically deal with it. Now there is this make syscall function that would do extra work. And then this syscall function. So let me show you here. No. Yeah, so then we created a custom thing that deals just specifically with syscalls. And I could remove it from the main handling of function literals. So previously function literals would know what syscall is and how to deal with it. Now it is a separate intrinsic that has nothing to do with regular function literals, which just means it should be a bit easier to separate it, because yeah, on some systems there is no such thing as syscalls at all. So why does the compiler have to know about them, right? It would be nice if you would just define them completely in userland, and this is more or less implemented. Like I could define it completely in userland, but right now it just would lead to a lot of code duplication, and I decided not to do it yet. Not interesting. It's just some metaprogramming and C interface stuff that is a bit annoying. I think this is just an if condition. Yeah, just an assert, more or less. Just a rename. So this one is a bit of a performance optimization. So whenever you have, like inside of expressions, you can have either if or yeah, so you have if expression or function literal that starts with fn keyword, and previously it was two functions, and there are still two functions, but sort of calling out to a function every time only for that function to say, actually, no, I didn't match anything, is kind of expensive. So with this commit, I just made it more direct. We always look at the first symbol, and if it is one of the symbols we care about, we dispatch it to the right function. This actually shaved off a bit of time from the compilation. This just does the same for the while loop. So in here, as you can see, now we have the while loop. My voice is getting a bit low, but I think there is not much to go, hopefully. So let's see. This is the last on this page. And oh, how many pages do we still have left? Yeah, so we have 2 pages left. Well, let's, hopefully I can survive till then. Let's take a look at this one. Correctly specify associativity for prefix separators. What it says in label, prefix separators more or less have right associativity. Only allow implicit casts of raw type to raw integers and floats. Yeah, so this was a problem when I said that raw types could be cast to anything of the same size. I realized that casting them to structs is a bit not what you want. So this just fixes that. You no longer can assign raw bytes to structs. This is just a nicer syntax. It wasn't working for some reason when I originally did it, so I had to do this string get. But after some changes, it seems to work perfectly fine. So now you can do a string dot and something, which I think is pretty neat. Separate function each. Yeah. So this is a precursor for a batch of changes that you're gonna see in the next commits. Essentially, what it's doing is you have this kind of function signature, and there are actually two versions of it in the compiler. First one is literally what the user wrote, right? And in this case, and the second one has explicit types deduced. In this case, everything is exactly the same, but if you have a function that's a generic, something like this, right? So we don't specify of type of this at all, and this one is a constraint type, but we don't know what it is. So in these cases, this is what literally is defined, but then there is a second definition of what was the exact descriptors for this for these parameters. And these change, like previously, both of those things would be stored in sort of the same type in function parameter. And this commit just introduced a separate type, result function parameter. And I think the only worthy thing here is to look at the actual definition of them in here. So this is just a more condensed down. So the literal has more variants here. It has more information, but this one is just a bit better packed, and it's it also gives more information to programmer that we transitioned from this kind of state to this kind of state. If you know about functional programming, there is this whole mantra of making invalid state unrepresentable, and this sort of goes in this direction of making sure that there is this second type that is a bit more precise, that is used to store sort of the same type of thing, but on a different stage in the lifetime of that thing. Okay. Simplify and clean up macro calls. So this was just yeah. This is a follow-up of one of the commits that we saw where I did the normalization of arguments, where, as you can see here, it refers to it. So the arguments that are statically known but of not the correct type are now cast outside of this code. So all of these things that dealt with casting just didn't have to be done anymore. Just reset storage, not interesting. Not interesting. This one is quite nice. Yeah. Just verify that I didn't miss the page. Whenever we try to match an overload, right? So whenever we say something like, whenever we try to match one of these, so we have a bunch of overloads. So we have overloads for all the types, and we matched one of them, and or we, more importantly, when we didn't match, or we matched too many. So if I call add of 34 and 2, and imagine I didn't have a specific overload for literals, which I do, but imagine I didn't, and I only had these kind of things. So what would happen here is these two literals are convertible to all the integer types, right? They would fit into any of them, so all of the overloads would match, and you would have 8 matched overloads. Previously, what would happen is we would just keep 2 of them, and it was sort of completely undeterministic which 2 were really kept. Like it would depend on the way it was defined and it was evaluated, and it was just a bit of a nasty thing. So you would end up with an error. First of all, errors could be different between different situations. So it wasn't good. In this change, I just decided that instead of 2, I'm going to keep a list of them. Where is the thing? Yeah. So you can see there were 2, match and previous best match that is conflicting. Now I just do match all of them. And then at the end in here, if we have more than one match, I verify, like I try to find the best match. And if I find the best match, but there are still more than one best match, then I just say, sorry, we found more than one. Where was... Yeah, this was collect. The next commit is report. So this just changes the error type. Yeah, this just changes the error type, I think, of this to do the right thing. Yeah. So previously there were, as you can see, there were 2. Now there were an array. There were no really more changes about it. It's just a purely error reporting thing. Remember the count of generic parameters in function literal. So previously it was a flag, as you can see, that just marked whether we had a literal like this, where we don't know what the arguments are, or a literal like this, where we do know what the types of all the arguments are. Now this is kept in a counter, and this counter is used to better judge what overload is better or worse. And there's going to be more on that in the next commit. Yeah, it's not interesting. Expect maybe default. Yeah, this is just an assertion removal, I think. Yeah. Instead of an if, we just have an assertion. So this is an interesting commit, and it's sort of a change to how this works. I will not read it out, just leave it on the screen. If you want, you can pause and do precise things, but essentially, I think one of the hardest things in a language is overloads is for the user to know what is happening when, right? To easily figure out what overload would be chosen and how to make the overload more or less desirable for choosing in the procedure or something like this. And previously it was just very messy. Now there is this very clear sort of set of guidelines, and you can understand what will win. I think it might result in a bit more clashes than was there before, but I, for now, decided that I would trade that for the clarity. The actual implementation is not that interesting, except that previously I would use like a score, where you just have sort of categories of matches, and let me find it. Yeah. So previously, if it was a generic match, then you would get score that. If it was an exact match, you would get score of that. And then at the end, you sort of sum up all the scores and you say, okay, this is a better match. But this has some weird implications about like what is better, what is worse. And I said it's just not easy for people to do that in their head. Whether with this new setup where I explicitly check for in this order, it's very easy. It actually ends up producing the same results, at least for the functions I have right now. So I think this is a very nice change, but only time will tell if I'm right. This is just an optimization of this procedure. There is nothing really much to look at there. This is more cleanup where it was started in one of the previous commits where we had, if you might remember, there was this split between dealing with pointers and dealing with literals, and then here, like, we know that something is a pointer or is a literal, so we specialize the code to that instead of having it generic with this wrapper function. This is the same. This is another thing about overload matching that is kind of interesting. So whenever you match a function call, so let's say this, right? You need to know in a regular language, the only thing you need to know is the types of arguments. In mass, you also need to know if the argument is static, you need to know the exact value of it. Previously, to make that happen, I would pass in the all full arguments to the function that would do the actual resolution of overloads. Where is it? Yeah, for example, here, right? Calculate arguments match score. It would accept a value view of arguments and it would do the resolution. Here, I change it to accept the previously added in one of the previous commits. So, you know, move in YouTube like 15 minutes before where we talked about the result function parameter. It would accept an array of those, which also can be either a descriptor or a static parameter, because some functions can have static parameters like what we have in here, right? So like we have it here, this is a static parameter. So we know exactly not just the type, but also the value of it when we are doing the matching. And this was actually awkward because if we needed to do just a match of two functions, like imagine what I have here when I have a function that accepts another function as an argument. Previously, what would happen is I would need to create fake values to be used as arguments just so that I could pass them on to do this matching. This commit actually flips it around, and in here, now whenever I match regular arguments, I actually create, somewhere here, I actually create a fake function, and I think this is way sort of more robust, and they are created in temp A, so it doesn't really matter, but just logically, I think it makes more sense than what was there before. Okay. This is next commit is pretty simple, but also pretty nice. In here, let me find the code. Yeah, a test is probably the easiest to look at. If we have some expression, and that expression we need to get not the type of expression, but what would be the type if that expression was used in the location where the type would be. So imagine I put this thing into here as a return type. So then the return type would be a struct, but it would be a type, not a struct itself. And this is a function or an intrinsic that does exactly that. And it's just useful in situation where you need to know, need to parse the type like that. Or the same would sort of happen, I think, with a function. Like if you put something like this in there, this would be a static struct of function header type. But if you want to have it be the actual type of the function, you need to do parse type on it. Unused stuff, not interesting. Let's try to blaze through more stuff here. probably handle empty space operator when right hand side has a custom parse. This is just a bug fix. Ooh. And the bug fix is essentially previously if I would have something like so if you have foo42, this is this apply operator, but previously if I had something like foo if x and then 1 else 2, then this will not be correctly parsed. And this just fixes this code. Explicitly typed local usage, not interesting. I'm slowly starting to get away from this kind of form, but I will probably have a separate video on it, so I'm not gonna talk too much about it here. Simplify some instruction pushing, just some cleanup, because now we have these nice literals. Fixed detection of fake argument used for return storage and call function arguments. Oh, yeah, right. This was just plain incorrect what was happening here. So this is a correct condition. Optimization, not interesting. Better cache key for generic functions. This is sort of interesting, at least from my perspective. You tell me what was interesting out of this video, if anything. Right. So what is happening here is, again, if I have a function, let me find something. I think allocate is the best example. So say you have a function like this. There are two things. First, this function is actually generic because it has this static or compile time parameter. And since it is generic, there will be actually multiple copies of it generated, right? So there will be a specialization, for example, where type is U64, there will be a specialization where type is string, and so on and so forth, right? So this is how generic functions work. But the thing is, we should not generate more than one copy of the function for each set of parameters. And previously, this caching was done on the types of the actual arguments that I used to pass to the function. So previously, like it would be like allocate, I don't know, my whatever, foo and string, right? And then you have foo and U64. So previously, these would be the keys for the cache. And this is bad because if you have a custom here or some other weird stuff, you would end up with duplicates. Moreover, I was only using the descriptors, so the types of the arguments, and I wasn't taking into account the statically known values. So this commit is addressing exactly that. As you can see here, previously what I said, it was matching against the descriptors, so just the types. And after the change, we also do this check over here where we actually match against the static parameter. So yeah, this was sort of a correctness change. It took me a while to figure out how this is supposed to work, but so far this has been really good. It has been very robust, and I'm kind of happy how this turned out. This one is something that is a result of previous one. So previous one enabled actually this. Previously, I would use macros in a bunch of places. This was just a remnant of whatever. I don't know why I was using it here. But in other places where I needed parameters to be compile time, I would use a macro, but now it's not really required. So static parameters are fully working. And that means that macros are, in a sense, not really needed. But we'll talk about it in a separate video because there is some stuff that still is interesting about macros. But again, that's going to be a separate video, so looking forward to that. Make a couple of tests not dependent, not interesting, short circle. Yeah, this is just an optimization, which is pretty obvious, but it was missing, right? So if types are pointer equal, they are the same type. And it was really, really nice to add. This is pretty much what it says on the label. So previously I would compare structs by pointer, but it was not correct after I added the brand thing, right? So if I want something to be compared essentially by pointer or by brand, then this is how it is. If I just do regular comparison of types, I will do it field by field. So if two structs have the same field and I have the same brand or don't have a brand, then they are the same. Okay, what is next? This is not interesting. So this is kind of stuff that is a bit awkward to do in C, to be honest. Essentially, I had this logic inside of assign tuple that we talked about before of remember matching the offsets and making sure that unions are correctly handled and things like this. But this was not actually used in a different place where we were figuring out if the types would match. So if we got to the point where we tried to assign, everything was working fine. But if we were just checking if we could assign something, then that would not work correctly, and this was a problem. So I could have either duplicated code or I had to come up with this thing where you pass in sort of two callbacks and then you can process it differently in different places. You can see here, like, I'm not actually using it in this code, but in here, this is one of the callbacks. So we would, in case of assignment, we would assign, and in the next commit, in commit next, is this the one? No, that's just cleanup. Actually, that's not important. Maybe. I think I got distracted by other stuff. And yeah, this is a follow-up commit to what we saw just now. So in here, now we call to the same function, we pass different callbacks. So this callback just recursively calls itself, and this now correctly handles tuples. So now I could assign more tuples to more things, essentially, and check them correctly. What was in here in between? Require intrinsic to return a value of the exact type. Yeah, so one of the reasons I was even working on this code is that I decided that I want to tighten up what could be assigned to what and what is implicitly cast to what. I think there's going to be a more precise commit about this stuff. But essentially, I'm just tightening it up. Previously, you would be able to have a cast in here, but now if you write an intrinsic, your intrinsic must return the exact type that it says it will return. More caching, more better, as it says in the label. 5 to 10% speed up is great, and there is nothing to it, essentially, just a hash map. And if we already did the processing of the intrinsic, we just get it from the hash map, and if not, we do the processing. Pretty standard stuff. Okay, so what is next? I think we are almost done with this page, which is great. There is only one left. Handle function deduction error outside of deduce runtime descriptor. Yeah, so previously, if we had two functions and we were not able to find the common type between them, this was an error, even in the cases where it shouldn't have been. So imagine I'm looking through a bunch of overloads, and those overloads take a callback. I'm trying to compare my function against that callback. This comparison fails, and suddenly the whole compilation fails instead of just going to the next callback, the next overload. This is all that is happening here. Okay, last page, just a bit more. Okay, more 64, not interesting. Only allow static and branded casts. Yeah, this is this tightening up of casts, and as it says here, the casts are sort of useful in two cases. The case number one is what we have roughly in here, where you have a literal and you're passing it to something of a number-like type. Right now it's just only integers, but later it could be also float technically. And this is very useful just because it is annoying to have to say here, I don't know, 8F64 or something like this, right? It's Rust, I think, forces you to do, and more or less C in certain cases. So this is very useful, but it's only correct if you know what the value is, right? Passing it an unknown type is a problem because there are only so many safe conversions, and it's very easy to shoot yourself in the foot. So I want to just disallow almost all runtime implicit conversions, but I still want to support compile time implicit conversions when we know the type of the literal and we can do proper testing of what is inside of that value. And this is just the same thing. So previously this was implicitly cast. Now it does a hard compare. The only thing that is allowed is if we have, for example, two structs and one of them is has a brand, another one doesn't have a brand, then it's allowed to assign them one to another. And this actually caught a few interesting little small things, like there is no longer a cast from a fixed array to a pointer like there is in C, and I think that's perfectly fine. Like this is a very unsafe operation in the first place, so it's good that it doesn't exist. But yeah. What's next? That's not interesting. Do strict type comparison. More on the same topic. Previously it was implicitly cast. Now you have to do exactly what it says, and it even got a small problem in tests where we were returning, like it was the same size, but it wasn't the same type, which was problematic. And here's the same thing, that previously it would implicitly cast to a pointer to avoid, now it doesn't implicitly cast, and I think, again, that's perfectly fine. Unlike C, in this language there are generics, so if you would want to do it more type safe, you can always add a wrapper function that would do this correctly. And just a bit more cleanup. Okay, next we have strict check-in of the macro types, more on the same topic. Previously it was implicit cast, now it's a concrete thing. Now we are not using this function at all, which is great. just a cleanup where this function was used only once, so why make it a function? Just inline it where it was called. Okay. This is sort of just more tests. I wasn't sure that this was working, but it was. If I try to call something that is static but still has the wrong type, that fails. It does fail. Everything's great. Yeah, right. So this is exactly, this is a cast from a literal. So again, if you have something like this, previously it was actually only allowing to cast to integer types, but also raw bit types, byte types are okay. So this makes that change. This is a custom case that sort of more or less exists in majority of languages that have pointers about the null. I think I will go the C++ way and eventually add a null pointer instead of just supporting 0 here. But for now, I didn't want to break everything, so I support passing 0 as a pointer. This is sort of interesting, where in certain cases, like it would be inconsistent which assignments would test the arguments, which assignments would not. And as you can see, once I added proper testing, that is the same as testing everywhere else, or to check in everywhere else, I ran into the same issue that we were passing an array as a pointer, and that's no longer allowed. I mean, it was obviously working because it was the same thing, but anyway, this was a good thing to implement because now just everything is more tight. I think this is a general sort of theme of the last months or so of me gradually sort of going through compiler and making sure that it's kind of robust, and I'm getting happy with where we're going so far. Remove some cleanup. Indirect argument handling during calls. Right, this is just using a helper that I had and I didn't use it. Early exit. Right. So this was sort of obscure condition that I was checking if something is already on the stack, then I probably don't need to copy it twice, but there is already a function storage equal that is more, it says on label, it's more robust. It always checks that if we are trying to copy the same thing to the same thing, then why are we doing that, right? That makes no sense. This one is pretty cool, I think. And that's something that was bugging me for a very, very long time. And I finally figured out how to deal with this. So let me find a good example of this. Well, actually here, that's perfectly fine. In Windows, or on Windows, if you have an argument, and that argument is a struct, or not necessarily struct, if that argument is larger than a register and it's not a float argument, then it is passed by implicit reference. So in C++ terms, it's like this, right? Or like this. So that you can use dot operator on this thing, but in reality, it is actually a pointer. For the first 4 arguments, this is actually easy to implement because these first 4 arguments are passed in the registers, and there is a special addressing mode in x86 where you can take the register and add some kind of constant to it. So you do something like, add rax, and then you say RBP plus 0, whatever, 20. So if my library name is passed as a pointer inside RPP register, which is not RPP, but doesn't matter. Let's say R9 to be more precise. If it's passed like that and I need to access a field of this struct, so I need to say library name.length, then I can just use this mode and do it in a single instruction. And this is just a regular operand. I don't have to care if it is in register or it is in memory. Like, I can easily do this. This was great. But then, and this was my first implementation of this. But then I realized that if you have 5 or more arguments and the 5th argument is passed like this, then the argument itself is passed on the stack. But this value on the stack is still a pointer. But I no longer can do this trick, right? I cannot in here say, like nested RSP plus whatever 12. I can't say that. So I can't do, I mean, in a sense I can. Well, no, not really. So I have to split it into 2 operations. I have to say that I want to move into some, say into R50, R14. I move these. So I move the pointer in here, and then I can use R14 to actually indirect this. And this is a problem because that's something that's just not representable in the compiler. I cannot say that something is stored like this. So this has been bugging me for a long time. My previous solution to this problem was to say that there is a special type that is implicit pointer, and it was stored like this in implicit pointer. And then there was a bunch of logic, as you can see. What happens when you try to assign it? What happens when you try to like do all kinds of stuff with it? Which was a very, very annoying thing to deal with, because you constantly had to remember, oh, is this pointer actually implicit or is it a real deal? It also was slowing down things, so it's like it was a mess. So I finally figured out what I wanted to do about this. And in this code, yeah. So this is the removement of implicit, but this is how it actually is handled. And the idea here is pretty simple. So in this version, I'm actually doing what I said first, where I just do sort of this kind of stuff, where it's already in register. I just handle this, and then there will be a follow-up commit which will show how I deal with it when it is on the stack. And this is this one, and it's kind of interesting. So I have this concept of a lazy value. That means that I will know what the value is at runtime, but not only that, I will tell you where this is stored only when you ask me. And this is done in, where are you? I think I accidentally committed it in the previous thing, but the idea is I added this is factory true, which means that when you ask me for the value of this, for example, library name, every time you ask me, I will actually load it from the stack and give you a register. And that means that you can very easily dereference that and do whatever you want. And sort of right now, it's more or less impossible to create implicit references, in the userland. So that's not a problem for anything besides the Windows and the 4th or later argument. So I'm fine to make this a bit less efficient than it was maybe before, in favor of these not having all of these cases everywhere. You can see it is very limited in scope, so it's a bit of code here and a bit of code in here. And compare that to what we had before, where you had all this logic in all the different places that had to care about this. Now all the logic is concentrated in just 2 places, and it makes me really happy because this is way more maintainable than what was there before, even if it is a bit more code, although I'm not sure. Okay, we are on the final stretch almost. A useless argument we can skip. We can skip this one, remove a couple, we can skip this one. This we also can skip. So this one is interesting and it goes in line with what I was saying before. So at some point I had, as you will see in a second, I had operator definitions in the mass code itself, just to see that I could. I moved everything out, everything was great. But then I realized it was actually causing problems, or not exactly problems, but it was causing me to slow down and make the compiler development slower. So until I actually need to have custom operator definitions, I just moved them back. And these allowed me to get rid. Yeah, it's the next commit. This allowed me to get rid of this whole function that dealt with defining operators in userland. And as you can see here, an interesting side effect of that is now I now have very few, namely one, custom statement matcher. And statement matcher is something that just runs on every statement in a block and tries to figure out if this is something very specific. And because I have only one statement matcher, I have this commit where now I don't need all of this thing where I have a list of them and I iterate over this list. Now I can call it directly, and in the next thing I can get rid of a bunch of other code that was dealing with the iteration of all the statement matchers and all this stuff. So the thing is, like, if you can inline code and remove abstraction, this is so enjoyable and so nice long-term for maintainability that it's usually worth it to take a temporary hit and maybe just a tiny step back to get rid of a lot of complexity if you can. This is not interesting. Right, so this was a bit of a problem where I would not be able to do this. Let me check. So previously, this would require an explicit cast. And this is silly because we know exactly what the value is. So why aren't we checking it? Now we do. So now that works. Okay, what's next? Next is this stuff. Right. So and this was a big fix me that I took care of. Essentially, what is happening here is that in a tuple, whenever you have something like this, that's fine. But if you have .foo, as we discussed, as just an enum thing, this is technically a statically known value, but it's not. How to explain? It is. Compiler knows what it is, but this is not of the right type. So when we are checking if the whole tuple is correctly static, this should report false in here because this is not a static value. So now instead of just a simple check for static, there is a separate function to deal with that. Okay, next. Fail casts of static values during... right, this is just an assertion for me, nothing really interesting. Just when I'm developing compiler, this should help catch bugs. So, just for left, let's see what happens. Yeah, so this is kind of nice. What this allows me to do is allows me to say that for particular operators, it is actually okay if they're missing the right-hand side of their operator. And in particular, this comes into play in here, as you can see, in returns. So return is an operator in this language. And previously operators would always require to have at least one value. So if it's a prefix operator, like return, you would need to put something here, and you could like put, previously you would force to put return and like this, if it returns a void, like this function. But that's not, it's not great. I mean, it's okay, but one of my goals for the language is to feel great to write, but at the same time be very consistent inside. And the idea they had is like, okay, well, what if I just say that for a particular operator, I can say, yeah, you don't have to have it, and the operator inside of it has to handle whether it is like a 0 argument or 1 argument for prefix, or whether it is 1 or 2 argument for infix functions. And this is exactly what it does, right? So here, for return, we can see that now it has this logic. Well, if it is has 0 arguments, then it returns void. Otherwise, it would returns whatever you passed in the argument. Pretty straightforward. Interesting consequence of that is it also works for infix operators. And as we saw, comma is an operator. So I can do the same thing for comma. If it has only 1 argument, then we just return whatever was on the left-hand side. If it has 2 arguments, where we do whatever we were doing before. And what that means in practical terms is that I can do this. I can add trailing commas and they work just fine. And I think this is again, it's not really a major feature or anything, but I think it just adds a bit of polish to the syntax. And I think it feels great that this is not like me going into a parser and saying, oh, okay, in this particular location in the parser, I can have a comma and I have to do all these rules. I can just very simply say, yeah, okay, for comma, it doesn't have to have a right-hand side, and if it doesn't, just don't do anything. It's literally like 3-line change, and I think this is great. Okay, what is happening here? Oh, yeah. I was still comparing things by pointer, and that's wrong, because types should be compared with the same type. And the final one for today. So this again goes into this thing of enums, what we discussed before. But before this change, it would only work for comparison. So I could say equals equals dot location, and that would work. Like what we have in std IO. So this would previously work, but this didn't. And then I realized that there is actually no difference between how something like this should be handled and how something like this should be handled. In both cases, we have a static value of a specific literal type, right? This is number in here, or I64, and here it's named accessor, what is called inside the compiler. but like conceptually they are exactly the same. It's a type, and when we are asking to if we can convert it to a particular type, they just do something, right? They do some checking. These checks that the sizes match, right? That we don't try to assign more bits than we have in the target type. And these checks if the target type has a field called location in it, in its own module. So this is what it does, right? I'm just doing the checking of the module and extracting it. Basically, I moved the code out of userland implementation and made it more general. Eventually, I hope to move this code again out of the compiler core. But again, as I said before, for now, I decided that making progress on the compiler is more important if I know I will be able to move it out, and I 100% know I will be able to move it out. Exactly how? Well, we'll see. There are various options, but for now, this provides a very nice syntax, and as you can see, there is a bunch of changes. It looks just much nicer than it did before. So yeah, I think that it wraps up for the day. That was a very long video. My voice is completely out, but I'm happy that I did it because it sort of shows you how much work is actually happening in compiler that you don't see. If you like the video and you would like to for me to do more of it, or maybe make some kind of suggestions, please write down in the comments, hit the like button, and subscribe for more content, you know, all the usual YouTube stuff. But that's it for me for today. Thank you very much for sticking with me so far, and hopefully see you next time.